Hello again. This is part 2 of Unit 1. In part 1, we talked about the Bayesian history a little bit, and then the steps of the scientific method, and then some differences between the frequency and Bayesian approach. In this part, we need to talk about some motivating examples that will help to understand how do we quantify the uncertainty in Bayesian approach and the frequency approach. And what do you mean by models? What do you mean by prior probabilities? And then the data, likelihood, and the posterior distributions or posterior probabilities. And I will show you that the Bayesian approach is sequential analysis. So you can update every time. Every time you get new data, you update the previous one and so on about the parameter you are interested in. So the National Cancer Institute recommends that women age 40 and above should have mammogram every 1 or 2 years. The mammogram produces X-ray images of tissues and the structure inside the breast and may help to detect and identify cancerous tumors. What does it mean, may? It means it is not accurate. It's not accurate 100%. It doesn't say this guy has cancer, this one doesn't have cancer. May help with some probability. It will say it has the cancer or not. There is nothing accurate 100% in this life. Everything with some probability is correct and some probability is incorrect. So assume that a friend was referred by her physician for her first screening mammogram. The friend doesn't have a family history of breast cancer, and before being referred for the screening mammogram, she had given no thoughts whatsoever to breast cancer and something that could conceivably happen to her. So the research question you have now, which is the first step in the scientific method, what her chances of being diagnosed with breast cancer? This is step number 1. So you need to see there is some available data or not. And maybe there is some data available can be answer the question, or the available information is not enough to answer the question. So Bayes' rule within the scientific method can be used to answer this research question. But before we answer the question, let's hold a little bit and discuss how do we quantify the uncertainty in Bayesian approach and frequency approach. We use probabilities all the time to quantify how much do we are sure about something will happen or something happen. So in science, in business, in daily life, people quantify uncertainty in the form of probabilities. Like the weather forecaster says there is a 30% chance of it gonna rain tomorrow or today. Or so we use probabilities all the time. That what is the probability it will rain after one hour from now, for example, and so on. There are 2 interpretations of probabilities, the long run and the subjective probabilities. So what is the long run frequency interpretation and the subjective probability? The first one, the frequency approach depends on the first one, and the Bayesian approach depends on the subjective plus the frequency approach. So let's see. 1 second. The long-run frequency interpretation, saying that the probability of a fair coin coming up heads is 0.5, means that we expect to get ahead about half of the time if we flip the coin a huge number of times. A huge number of times. So it is 0.5. It doesn't mean if I flip the coin only 10 times, I will get 5 times the head, 5 times the tail. It means if I did the experiment many times, I will get 50% of times head, 50% of time tails. This is the long-run interpretation of the probability, like 0.5. The interpretation is useful and frequency approach is based on it, but in many situations, we cannot use the long-run interpretation. For example, in 2007, 2008, editorial writers were assessing the probability that the United States economy was headed for a major recession. How do we answer this question using the long run? Using the long run probability is not easy, because it is obvious that this question could not be answered as the proportion of times that the country is facing exactly the economic, social, and political conditions that existed in the United States. I mean, it's not easy to find how many countries have the same situation, everything like the social and the political and economic situations, and then count how many of them headed to a major recession, and then divide by the total number, we get the probability. This one is not easy to find, so you should depend on the subjective probability. So subjective probability is a probability of an event or the truth of a statement is a number between 0 and 1, like the long run is between 0 and 1 also, that quantifies a particular person's subjective opinion as to how likely that the event is occur or how likely the statement is to be true. So we depend on our beliefs, we depend on our experience to assign some probability. That probability is subjective probability. Suppose that I tell you that I have carried out a study consisting of 6 trials. Each trial has 2 possibilities, success and fail. I believe that the probability of success was the same of each trial, and they are independent. The outcome was 6 successes in 6 trials. So every time I get success, 6 times. So what is the prediction of the outcome number 7? Or what is the probability of getting success in the trial number 7? If I asked you this question, most probably you will give me different probabilities. Like when someone will say, with probability 1, because I got 6 successes. So for sure, like the number 7 will be success. Maybe someone will say, no, they are independent. So maybe the number 6 is the success is 0.5 and failure is 0.5. So someone will say, I think it is higher than 0.5, like 0.6 or 0.7. So now you depend on your experience to assign some probability for the trial number 7. This is subjective probability. Whatever you use the long run or the subjective probability, you need to keep in your mind that there are 2 properties for probabilities. The probability never be negative. The probability must be positive. Sorry. The probability must be positive or greater than or equal 0, non-negative. The sum of all the probabilities is 1. The sum of the probability of all the outcomes is always 1. So the probability of any event is greater than or equal 0, and the sum of all the probabilities is 1. These 2 probabilities are satisfied whatever you are working with subjective probability or frequentist approach probability or long-run probability. So let's go back to our example. For the friend, there are 2 possible true states. She has cancer or she doesn't have cancer. We need to know the probability of having cancer and the probability of doesn't have cancer. But we are interested in the first one, like the probability of having cancer. So before obtaining any data, let's see, maybe there are some available data, available information can be used to calculate the probability of cancer. So before obtaining any data about your own breast cancer, it should be rational for the friend to figure that her chance of being discovered to have breast cancer is similar to that of randomly selected a person in the population of all women who undergo screening mammogram. So her chance to have a cancer looks like it or equal to the probability of randomly select one of the person who have had this mammogram test. And among those guys have taken this mammogram test, how many they diagnosed cancer, how many is not. So we divide the number of people have cancer and divide by the total number. So we get some kind of probability of having cancer as well. Based on published studies, the proportion of women who are diagnosed with cancer within 1 year is about 0.004. It means 4.5 per 1,000. Therefore, the friend assigns the following prior probabilities. Those are the current information, or the current probabilities, or the prior probabilities for the two cases. So now we can say the friend has probability 0.0045 to have a cancer, probability 0.9955 doesn't have cancer. But those are the current information or the prior probabilities. So if this information is enough, it's fine, but this information is not enough to answer the question. So we need to go the step number 3, because note, this is step number 2 in the scientific method. Those are the prior probabilities, the available information, the previous information that refer to probabilities assessed before new data gathered. So we need to collect more data. When you collect more data, you will update these prior probabilities by the new information. So the data, because the Zoom, the title of these kind of menus is headache for me. Okay. The data and likelihood. The information in step number 2 of the scientific method is not enough. New information need to be collected by having the mammogram test. So we go from step number 2 to step number 3. So the following are the possible results of mammogram. The mammogram test may be positive. Come on. Maybe positive, maybe negative. If it is positive, the mammogram indicates possible or likely cancer. Negative means the mammogram doesn't give any evidence of cancer. So if you work with notations, C+ means cancer, C- doesn't have cancer. M+ means the mammogram is positive results. M- mammogram is negative results. So for perfect test, the probability of M+, C+, come on. The probability of M+, C+ would equal to 1. And the probability of M+, C- should be 0, but nothing perfect in this life. If probability of M+, C+ is 1 and the probability of M+, C- is 0, it means for sure if someone has cancer, the results will be positive. And for sure if someone doesn't have cancer, the probability of M+ is 0. But this one is not the case. There is nothing perfect in these lives. There is no test is perfect. So a study of tens of thousands of people who received the screening mammogram found that if a person doesn't have cancer, then the probability that the screening mammogram will be positive is only 0.724. It should be 1. And this means the probability of M+ given C+ is 0.724. And it is found that the probability of M+ given C- is 0.027, which it should be 0, but it's not 0. The complement of these two probabilities, the probability of M minus given C minus, this one is the complement of this one, and the probability of M minus C plus, this one is the complement of this one. So now we have new information. Now we collected new information. And after the friend takes the mammogram test, if it is positive, we will update the prior probabilities by the positive probabilities. If the mammogram is negative, we will update the prior probabilities using the negative probabilities, negative result probabilities. So we can summarize this information. Those are the prior probabilities, and those are the probabilities of mammogram plus. This is the probability of mammogram results is negative. After the friend takes the mammogram test, you will get the results. If the results is positive, we will update these ones by these ones. If the mammogram is negative, we will update these probabilities by these probabilities. So what is the friend the chance of being diagnosed with cancer given all this information? So let's see the results. In general, we use the Bayes rule to update. We need to update the prior probabilities by the new information, or the new probabilities, or the likelihood probabilities, or the probabilities we collected, and so on. We use the Bayes rule, the mathematical rule, for using data to update one's probabilities about models. The likelihood associated with the particular model is the probability of the observed data under that model. And the Bayes rule is this one. This is the probability of model. This one is called the prior probabilities. We multiply the prior probabilities by the likelihood. This one is called likelihood function. So this is the new information, and this is the previous information. So we multiply the prior probabilities by the likelihood, and then we get something proportional to the probability of the model given data. This one is called posterior probabilities. So the posterior probability is proportional to the multiplication of the prior probabilities times the likelihood. So this one is called the Bayes theorem. You will see this one many times during the semester. And this was called Bayes theorem, or the Bayes rule, that converts the likelihood and the prior into posterior. So the posterior distribution, or the posterior probabilities, have the information from the prior and the information from the likelihood, or from the current data. So let's assume that the mammogram results for the friend is positive, and find the updated probabilities. So if it is positive, we will update the prior probabilities by the positive one. Those are the two positive probabilities. So you multiply this one by this one by this one, you get these two probabilities. Keep in your mind, those are not probabilities. Those are proportional to the posterior probabilities. So what do you mean proportional to the posterior probabilities? It means they are not probabilities. You need to change them to be probabilities. So how do I change these two to be probabilities? You calculate the sum. This is the total, this one plus this one. And then you divide these two values by the sum. You get two values. And these two values are probabilities. The sum is 1. So now, after the mammogram is positive, now I can say the probability, or the updated probabilities, or the posterior probability of having cancer is 0.107, and the probability of having no cancer is 0.893. The probability of, although the mammogram is positive, but the probability is not 1. The probability is 0.107, but increased. But this one increased from 0.0045 to 0.107. It is increased 24 times. Looks like we need to do something else. We need to follow up the analysis. We need to collect more data to make sure the friend has cancer or not, because 0.107 is not a small value. So we need to collect more data and update these current one. Now those are the current one. And if we collected more data, we will update these ones. These ones will be prior probabilities now. And then we update them to a new posterior probabilities. So because the probability is not small, at her doctor recommendation, the friend underwent a procedure called the SCNP. And the SCNP is a procedure in which the mammographic methods are used to get some cells, a sample from these cells, and then examine these kind of cells to make sure there is some cancer or not. If cancerous cells are observed, the test is considered positive. If there is no, it will be considered negative. So now we need to do these kind of tests and then update the probabilities one more time. According to this published paper, the probability of S plus given C plus is 0.89. It should be 1, but it's 0.89. And the probability of S minus C minus is 0.94. It should be 1, but it is not 1. Nothing perfect in this life. So the probability of S plus C minus is 0.06. This is the complement of this one. And this one is the probability. The probability is 0.11, which is the complement of this one. So now we have new information. Now we can update the posterior distribution, and we will consider these two guys are prior probabilities now. And when then we update those ones based on the new information. So let the friend take this kind of test, which is, I don't like these kind of things. And let's ask the friend to take this test and then update the current probabilities. We will update these current probabilities by these two, this one and this one, if the test is positive. We will update by this one and this one if the test is negative. So after the mammogram, the friend's current probabilities were the posterior probabilities based on the mammogram. These become her prior probabilities with respect to the new data obtained from the new test. And the Bayesian analysis in which accumulating information is incorporated over time, with the posterior probabilities from one step becoming the prior probabilities for the next step. This one is called Bayesian sequential analysis. This one is not easy in the frequency approach. But in Bayesian approach, we can update all the time. Every time you get new data, update the previous one, update the previous one, update the previous one, and so on. So the Bayesian approach is sequential approach, and the update is very simple. So let's assume the test of the friend was negative. So the test is negative. It means I will update the previous posterior probabilities, which now considered as prior probabilities, by the negative probabilities. So the prior probabilities now are 0.107, 0.893, and the likelihood for the negative is 0.11, 0.94. So let's multiply this one by this one. You get these two likelihoods. Those are not probabilities. You need to change these two to be probabilities. So you calculate the sum, and then you divide these two values by the sum. You get two probabilities. The sum is 1. Those are the posterior probabilities. Now the probability of cancer decreased to be 0.014. and the probability of not cancer increased to be 0.986. And because the probability now is very small, so the physician, sorry. So now the physician can ask the friend to come next year or after 2 years to take the test again, because now the probability is very small. But if we find the test is positive, in this case, we will update these two prior probabilities by the S plus. So let's assume the result is positive. So what is the posterior probability of having cancer? So it means I will update these two prior probabilities. These two prior probabilities, 0.107, 0.893. I will update these two by the S plus, given model or given the two cases. I will update these two by 0.89 and 0.06. I will multiply these two, this one times this one. I will get something called the likelihood. Likelihood times the prior. And if 0.107 times 0.89 is 0.9 or 0.09, 523, and 0.893 times 0.06 is 0.0335, those are not two probabilities. These two values proportional to the posterior probabilities. So let's change them to be posterior probabilities. You calculate the sum, 0.14881, and then you divide these two values by the sum. You get the updated probabilities or the posterior probabilities. So the first one is 0.6399, 0.3601. The sum of these two probabilities is 1. The first one is the probability of cancer. The second one is probability of no cancer. So now we can see the probability of having cancer is very big. So now maybe the physician will ask the friend to have some surgery, because the probability is very big. It's very big, but it's not 1. So it's still 0.6, but it's very big probability. So they will do some surgery and make sure there is some cancer or not. So this is how to update the probabilities in Bayesian approach. Every time you have new information, you update the previous one, and so on. So in this unit, we provided a brief introduction to the scientific method, and we are familiar with what do you mean by subjective probability, how the Bayesian approach uses data to update people's knowledge. And then we will go to the unit number 2. And the unit number 2 is easy one. Most probably many of you have heard about, but we need to cover this one because it is the base or the basics of the Bayesian or Bayes rule. So we will review the concepts of probabilities, like the probability of union, probability of intersection, and conditional probabilities, marginal probabilities, and so on. And we will end up by something called Bayes rule in the discrete case. So, and we will you will see this formula, which is the probability of the posterior probability proportional to the prior probabilities or the prior belief about something times the likelihood, and then you change it to be posterior. You will see this one a lot during the semester. So please, if you have any question at any time, please do not hesitate to contact me. I will be more than happy to help. So if you have any question, let me know. you can stop by the Zoom, the weekly Zoom meetings and ask your question, or you can send me email or any convenient way to you. So thank you so much. And let's go to the unit number 2. Thank you. Have a great day.